Students, we know that everything in this universe is made up of matter. The air we breathe, the food we eat, stones, clouds, plants and animals, etc. We also know that atoms and molecules are the fundamental building blocks of matter. Now look at the stone and the water. Are they identical to one another? No, they are made up of different kinds of matter. So, the stone and the water are two different kinds of matter. This is because different kinds of matter is due to different atoms constituting them. Now, the question is, what makes the atom of one element different from the atom of another element? Are atoms really indivisible as proposed by Dalton? Or are there smaller constituents inside the atom? We shall find out the answer to these questions in this video. Charged particles in matter. For understanding the nature of charged particles in matter, let us carry out the following activities. Comb dry hair. Thus the comb then attracts small pieces of paper. Rub a glass rod with a silk cloth and bring the rod near an inflated balloon. Observe what happens. From these activities, we can conclude that on rubbing two objects together, they become electrically charged. Where does this charge comes from? This question can be answered by knowing that an atom is divisible and consists of charged particles. It was known by 1900 that an atom was not a simple indivisible particle, but contained at least one subatomic particle, the electron, identified by J.J. Thomson. Even before electron was identified, E. Goldstein in 1886 discovered a subatomic particle which had a charge equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of the electron. It was given the name proton. In general, an electron is represented as E negative and proton as P positive. The mass of proton is taken as 1 unit and its charge as +1. The mass of an electron is considered to be negligible and its charge is -1. It seems highly likely that an atom was composed of protons and electrons, mutually balancing their charges. It also appeared that the protons were in the interior of the atom, for whereas electrons could easily be peeled off, but not protons. Now, the big question was, what sort of structure did these particles of the atom form? For explaining this, many scientists proposed various atomic models. J.J. Thomson was the first one to propose a model for the structure of an atom. J.J. Thomson, 1856 to 1940, a British physicist, was born in Cheetham Hill, a suburb of Manchester, on 18 December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. Thomson's model of an atom. J.J. Thomson proposed that an atom consists of a positively charged sphere. the negatively charged particle, that is, electrons, are embedded in it. It is similar to that of a Christmas pudding. The electron in a sphere of positive charge were like currants, dry fruits in a spherical Christmas pudding. We can also think of a watermelon where the positive charge is the red edible part in the watermelon and the seeds are the electrons. Thomson also stated that the atom is electrically neutral as the negative and positive charge are equal in magnitude. Although Thomson's model explained that atoms are electrically neutral, the results of experiments carried out by other scientists could not be explained by this model.
Ernest Rutherford, 1871 to 1937, was born at Spring Grove on 30th August 1871. He was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Let a child stand in front of a wall with her eyes closed. Let the child throw stones at the wall from a distance. She will hear a sound when each stone strikes the wall. If the child repeats this 10 times, she will hear it 10 times. But if a blindfolded child would throw stones at a barbed wire fence, most of the stones will not hit the fence, and so no sound would be heard. Rutherford also did a similar kind of experiment as shown in the video, as he was interested in knowing how the electrons are arranged within an atom. So in his experiment, fast-moving alpha particles were made to fall on a thin gold foil. The alpha particles are doubly charged helium ions having mass 4 times that of a hydrogen atom. And the gold foil was about 1000 atoms thick. On performing this experiment, Rutherford observed that most of the fast-moving alpha particles passed through the gold foil. Some of the alpha particles were deflected by the foil by small angles, indicating that there is some positive center present in the atom, which deflects the alpha particles. This positively charged body in the center is the nucleus. Only 1 out of every 12,000 particles appeared to rebound based on this experiment. So Rutherford concluded that an atom consists of a positively charged center, the nucleus. The electrons revolve around the nucleus in circular paths. The size of nucleus is very small as compared to the size of the atom. Drawbacks of Rutherford's model of the atom. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable.
Bohr's model of an atom. Bohr's model was proposed by Niels Bohr. Niels Bohr was born in Copenhagen on 7 October 1885. He was appointed Professor of Physics at Copenhagen University in 1916. He got the Nobel Prize for his work on the structure of an atom in 1922. In order to overcome the objection raised against Rutherford's model of the atom, Niels Bohr put forward the following postulates about the model of an atom. Only certain special orbits, known as discrete orbits of electron, are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate energy. These orbits or shells are called energy levels. These orbits or shells are represented by the letters K, L, M, N, or the numbers N is equal to 1, 2, 3, 4.
We'll discuss about distribution of electrons in different orbit of an atom. Bohr suggested 3 rules. So we'll point out those 3 rules here. Rule number 1. He said the number of electrons in an orbit will follow this 2n square. So in that case, in case of first orbit, n equals to 1, that means the K cell. The number of electrons will be 2n square, that is 2. In case of second orbit, that is the L cell, the number of electrons will be in case of third orbit, that is the M cell, the number of electrons will be likewise. We can calculate the number of electrons in the orbits n equals to 4, 5 or 6 and so on. So the number of electrons in different orbits are different. But rule number 2 says the maximum number of electrons in the last orbit, the outermost orbit, is 8. Rule number 3 says electrons can be accommodated in any given cell only when the previous orbit is completely filled. So in order to fill any orbit, in order to accommodate electron in any orbit, the previous orbit should be filled completely. Now we'll see how the electrons are distributed in different elements. We'll take first hydrogen atom. In hydrogen atom, the number of electrons is 1 only. So because the first orbit, the first cell, that is K cell, can accommodate maximum 2 electrons, here the electron of hydrogen atom will be accommodated in the K cell only. So the number of electrons in K cell will be 1 and there will be no other cell in hydrogen atom. So the atomic structure of hydrogen atom will be like this. At the center there will be nucleus and 1 electron will be there in K cell or n equals to 1 orbit. Now we take helium atom. In case of helium, the number of electrons is 2, and as we know, the K cell can accommodate 2 electrons. So the electrons will be accommodated in the K cell itself. And if we draw the atomic structure of helium, it will look like this. At the center there will be nucleus and 2 electrons will be accommodated in the K cell. And K cell will be filled completely and there will be no other cells. Now we take chlorine atom. There are 17 electrons in chlorine atom. So the first 2 electrons will be accommodated in K cell because K cell can accommodate maximum 2 electrons, and 8 electrons will be accommodated in L cell because the L cell can accommodate maximum of 8 electrons as per the formula 2n square, where K is n equals to 1 and L is n equals to 2. So the next cell can accommodate 7 electrons, that is the M cell, which is n equals to 3. N equals to 3 can accommodate maximum of 18 electrons as per the formula 2n square. And so chlorine, the 7 electrons, the last 7 electrons can be accommodated in the M cell. So now if we draw the atomic structure of chlorine, it will look like this. At the center there is a nucleus and the first orbit, that is K cell, which will accommodate 2 electrons, and the next orbit, that is L cell, which will accommodate 8 electrons, and the last orbit, that is the M cell, will accommodate 7 electrons. Now we take the example of sodium atom. Sodium has total 11 electrons. So the first 2 electrons will go to K cell, that is n equals to 1 orbit. Next 8 electrons will go to L cell, that is n equals to 2 orbit. And the rest 1 electron will go to M cell, that is n equals to 3 orbit. So if we draw the atomic structure of sodium, it will look like this. At the center there is nucleus, then the first 2 electrons will be distributed in K cell. 8 electrons will be accommodated in the L cell, and 1 electron will be there in the M cell.
We have already learned how the electrons in an orbit are arranged in different shells, orbits. Also, the maximum number of electrons that can be accommodated in the first orbit is 2, and thereafter the outermost shell of an atom can accommodate a maximum of 8 electrons. Now, why is it that the atom of some elements like helium, argon, etc. show little chemical activity? To find out the answer, let us understand the concept of valency. The atoms of elements which show little chemical activity are stable. It means that their outermost shell is completely filled, that is, the inert elements like helium and argon. Since the maximum number of electrons that can be accommodated in the first shell is 2, and the atomic number of helium is 2, it is completely filled and is stable. The atomic number of argon is 18, and so the electrons configuration is 2, 8, 8. The outermost shell is completely filled and is stable. Thus, elements like helium, argon show less chemical activity. The chemical activity is determined by the tendency of atoms of one element to react and form molecules with atoms of the same or different elements. Now, what happens if the outermost shell of an atom is not completely filled? There is losing, sharing, or gaining of electrons in order to make the octet of electrons in the outermost shell. Let us take an example of a duet song competition organized in your school. Lily, Sita, and Suhana wants to participate in the competition. Lily and Sita forms a duo, and now for Suhana to participate in the competition, she will have to form a duo. So Sita agrees to accompany Suhana and perform with her as well. In this case, Sita is being shared by Lily and Suhana. Similar is the case when carbon and hydrogen atom are combined. Now, for carbon to fill its shell, it will share one electron each with 4 hydrogen atoms and thus form a bond. This is how electron sharing takes place between atoms of different elements. Let us take another example of 2 groups of children. In order to participate in a dance competition, there should be 8 members in a group. Here, Group A has a total of 6 members and Group B has a total of 10 members. We see that Group A has 2 members less, whereas Group B has 2 members more. Now, 2 members from Group B can join Group A in order to have 8 members in each group. Here Group A is gaining, whereas Group B is losing. Similar is the case with elements, say like oxygen. The atomic number of oxygen is 8. So, its outer orbit will have 6 electrons. Now, in order to have 8 electrons in its outermost shell, 2 more electrons need to be gained. So this is what we call a valency. Here, valency is 2. Now, let us take the example of magnesium. Its atomic number is 12. Electronic configuration is 2, 8, 2. We see that for the outermost shell to be filled, 6 more electrons need to be gained. Does it mean that the valency is 6? Well, it could be, but we see that it is easier to lose 2 electrons than to gain 6 electrons in order to have an outermost shell filled. So, in this case, magnesium will lose 2 electrons to be stable. Hence, the valency is 2. So, we have seen that atoms would react so as to achieve an octet in their outermost shell. This is done by sharing, gaining, or losing electrons. We know that everything in this universe is made up of matter, and atoms and molecules are the building blocks of matter. After the subsequent discoveries of atomic model by J.J. Thomson, Rutherford, and Niels Bohr, and the discovery of neutron by Chadwick, now we know that the atom are made of negatively charged electrons and positively charged protons, and neutrally charged neutrons. There is a very positive region at the center of the atom. This is called the nucleus, where all the protons and neutrons stay together. As discovered by Chadwick, mass of neutron is almost the same as the mass of proton. The electrons are very much lighter than proton or neutrons, and they revolve around the nucleus in orbits. So, almost all the masses of the atom are concentrated in the nucleus, which makes the nucleus a very small and heavy region inside the atom. Now, how many protons are present in the nucleus of an atom determines its atomic number and is represented by Z. This number decides the type of the element as well. For hydrogen, Z is equal to 1, that is, 1 proton present in the nucleus of hydrogen atom. For carbon, Z is equal to 6. Therefore, 6 proton is present in the nucleus of the carbon atom. Now, how is the mass of an atom determined? Therefore, the nucleus of an atom consists of protons and neutrons. So, the mass is determined by adding the number of protons and neutrons. Protons and neutrons, that is, the mass number, are also called nucleons. Can you see what is the mass of a carbon atom? It has 6 protons and 6 neutrons, so its mass is 12. Is there any notation for an atom? Well, it is written as for example, nitrogen is written as. Now, what about hydrogen atom? Its atomic number is 1 and mass number is 1. Then one type of hydrogen atom can be written as. Did I say one type of hydrogen atom? Yes, because hydrogen atom has 3 atomic species: protium, deuterium, and tritium. We see that the atomic number of each is 1, but the mass number is different. That is 1, 2, and 3. Let us take another example, say carbon atom. Here, the atomic number is 6, and mass number in both the types are different. That is 12 and 14. Similarly, for chlorine, we have So, on the basis of these examples, we can say that there are 3 isotopes of hydrogen, 2 isotopes of carbon, and 2 for chlorine. That is, isotopes are defined as atoms of the same element having the same atomic number but different mass number. The chemical properties of isotopes are similar, but the physical properties are different. Now, the question is, what should we take as the mass number? If the atom of the same element has different mass number, the answer is that we have to know the percentage of each isotopic form, and the average mass is calculated. Example, in the case of chlorine atom, there are 2 isotopic forms with masses 35 and 37 in the ratio of 3:1. So, the average atomic mass of chlorine atom is This does not mean that any one atom of chlorine has a fractional mass of 35.5. It means if we take a certain amount of chlorine, it will contain both isotopes of chlorine and the average mass is 35.5. Now, let us discuss about isobars. Let us see a calcium atom and an argon atom. Here, the mass number, that is the total number of nucleons, is the same in both calcium and argon, but they have different atomic number. So we can say that atoms of different elements with different atomic number and same mass number are known as isobars.